In this video, we're going to look at how we can convert the generalized expression of KEQ, the concentration of all of a reaction's products, divided by the concentration of all of that same reaction's reactants, into a usable mathematical expression that we can use to calculate specific concentrations of specific products and reactants within a given equilibrium system. So if we look at how to come up with this usable expression, we can use this generalized equilibrium system here. So we know that our products are C and D. So in our KEQ expression, we would simply write concentration of C times the concentration of D. And since A and B are the reactants, we would write concentration of A times the concentration of B. For the observant among you that caught that the lowercase letters represent stoichiometry coefficients, we will put this on hold and revisit it later after seeing how to deal with it in an actual KEQ expression. So if we look at this reaction here, this is a relatively simple equilibrium system where the stoichiometry coefficient of every one of the reactants and products is 1, so it should be fairly straightforward to write. So we know our products are fluoromethane and chloride, so we would simply write concentration of fluoromethane times the concentration of chloride, and we would divide by the concentration of our two reactants, concentration of chloromethane times the concentration of fluoride, and that is that. Now we can start off the same way by writing this form of the expression for the synthesis of ammonia. So the concentration of ammonia, because it's our only product, divided by the concentration of our two reactants, nitrogen gas and hydrogen gas, multiplied by each other. So now comes the question, how do we deal with the stoichiometry coefficients? When converting a reaction of an equilibrium system, the stoichiometry coefficients simply become exponents within the KEQ expression. So because ammonia has a stoichiometry coefficient of 2, we would put a squared sign here, and because hydrogen has a coefficient of 3, we would put a cubed sign here. So if we go back to our generalized expression, we can simply take all of our stoichiometric coefficients and apply them as exponents to each of the reactants and products, such as this. Now, unfortunately, writing equilibrium expressions or writing KEQ equations is never quite that simple, as we'll see with this reaction here. So for the first time, we actually see that there is a solid in our equilibrium system. So if we were to write out the KEQ expression for this, normally it would be quite straightforward. We have two products, so we would represent these with concentration of calcium 2 plus ions times the concentration of fluoride ions, and we would take this coefficient of 2 and write a squared above the concentration of fluoride, and then because we only have one reactant, we would simply write the concentration of CaF2 like so. Except if you think about the definition of concentration, that being the moles of solute divided by the volume of solvent if we're dealing with aqueous compounds, or the volume of the container if we're dealing with gases, this definition makes no sense for calcium fluoride because calcium fluoride is a solid, meaning there is no solvent and there is no container that affects the volume. Therefore, we can consider that the concentration of CaF2 and any other solid is going to be constant, which we can show with a simple mathematical relationship. If we take the mass of a given substance divided by the volume that that substance occupies, we know that this is the formula for density, and if we multiply it by the number of moles of a given substance, or rather the mass of that substance, or the mass of 1 mole of that substance, also known as molar mass, we can see that if we take the density of a given substance and divide it by the molar mass, remember that division is just the same as multiplying by the reciprocal, we see that the mass of the substance cancels each other out, and we end up with moles per liter. Now, we know that the density and the molar mass of any given substance, as long as we're on Earth, are both going to be constant, and therefore that the concentration of that solid, because concentration of a solid is simply derived from the molar mass and the density, we know that that concentration is going to be constant as well, and therefore this is not a variable, which means that we can simply move this over and incorporate it into the value of KEQ itself. And therefore, writing out the KEQ for this expression here would simply be the concentration of calcium ions times the concentration of fluoride ions squared, and the constant concentration of the solid, we would simply multiply both sides by it and incorporate it into KEQ, the equilibrium constant itself. This is also true for liquids for the same reason. Now, if we go back and consider what the formula for concentration is, the moles of solute divided by the volume of the solvent, if you have a liquid, you have no solute, so the idea of concentration makes no sense. So if we only have one liquid within the reaction, there is no meaningful way to measure the concentration of a liquid unless we compare density and molar mass. Now, if the liquid is the only liquid in the reaction, it is what we call a pure liquid and is not written in the KEQ expression for the same reason. So if we were to write the KEQ expression for this acid ionization here, we would not write the concentration of water at all, because we know that water is our solvent, and again, there's no meaningful way to measure its concentration because it's constant. So if we were to write out the KEQ expression for this reaction here, we would simply write the concentration of our two products multiplied by each other, so concentration of acetate times the concentration of hydronium, and divide that by the concentration of our only reactant solute, which is the concentration of acetic acid, and water's concentration is not included in this because it's assumed to be constant. There is one exception to this, where liquids are not considered pure if there is more than one liquid that can dissolve other liquids. So for example, we know that ethanoic acid in this case is actually a liquid at room temperature. Another example of this would be alcohol. So if we wanted to write out the chemical formula for the alcohol that most people know of, CH3CH2OH, we know that this is a liquid at room temperature, and we know that it dissolves when it is put into water. So in this case, liquids are not considered pure when there are multiple liquids that can dissolve one another, and in which case the liquid that is the smaller volume therefore becomes the solute. And that's why, even though ethanoic acid is a liquid at room temperature, we would write it as aqueous because it's considered a solute because it's dissolved within water like this. So now that we have a general idea about how to write KEQ expressions, in the next series of videos, we're going to look at how to use these expressions in order to calculate specific concentrations of reactants or products in equilibrium systems.